Okay, well, I guess we'll start. Welcome to the Robotics Seminar. Our honored guest today is Vincent Hayward. Did I say that correctly?
Yes.
I've actually known Vincent for I don't even know how long. So when I first got my PhD, Vincent was working with a famous guy, maybe sort of, in my mind, he's kind of the #1 guy in manipulator systems, Lou Paul at Purdue, and they had this thing called RCCL, the Robot C Control Library, and they would give it to anybody that wanted to use it. Yeah. And it was open source.
Yeah, yeah.
And so this is really the first open source project that I ever knew about, and it was a really great service because industrial arms ordinarily are just locked up as tight as can be, and as you know, if you've worked with them, that's a big handicap. So that was a really great project. Somehow, 30 years later, he's now got this fascinating work in haptics. And so for me, that's a kind of interesting. Those two things seem pretty far apart. But let me think. Formally, he's a professor at UPMC, which does not mean University of Pittsburgh Medical Center. It means Université Pierre, Marie Curie.
You'll be hearing from their lawyer.
And it's done a lot of interesting things in between. Spent a lot of time at McGill. So I'll turn it over to you.
Thank you.
Join me in welcoming the speaker.
So thanks for the anecdotes. And I'll, as Matt has explained, I am interested in haptics, which was defined a century ago essentially as the phenomenon of hand guidance by touch. That's how it was defined, and it covers different topics. Studying haptics is like studying vision or audition. You can be interested in all the way from molecules to systems. It's a series of very complicated, interesting phenomena which govern manipulation, essentially, and locomotion. And so today, I made a selection of certain works I did and some others on the mechanics of the hand and how, or the fingertip or the skin, and also maybe at a smaller scale. And how that has apparent consequences on the fact that we or the animals can feel their world mechanically and guide their movements through that. So that's the general idea. There's a number of logos here. When I came back to France 5 years ago from McGill, as Matt explained, like all the academics, I started writing lots of grants and got them all. So the result is that there's been a lot of, I had a big lab for these five years, much bigger than I actually could really handle, but it's a good lab. There's a lot of interesting equipment and stuff going on now. And so I want to explain what these logos mean, because that would take too long. And I'll just remind you that the hand is something which is fascinating, and it's just as important as the brain. And in fact, you cannot really understand the hand without the brain without the hand. They are really part of the same system, and that is intuitively known by the society. And so what you see here is like a close-up view of what you have inside the hands. So inside the hand, you have what's called the volar part, the volar region, which is the one that comes in contact with the manipulated object. And it's actually quite different in many ways from the skin that you have elsewhere. okay, in the rest of your body. And also very different from the skin that you have inside your mouth, which is the mucus type skin, which is also highly sensory capable. I mean, the mouth is wonderful in terms of detection and manipulation of small things. But somehow the hand that we have are good for manipulation, and it owes this capability to a neural system, which is represented on that slide, but I won't explain today too much about it. All I would like to say, and that's also which matters at this point, is that most of the neural equipment that's in the skull is essentially detecting changes in the mechanical state. And so that's what physiological phasic system, it really is sensitive to modifications. And that's what it's really tuned for. And that is very true at many levels of the organization of the sensory motor system. But what is very interesting is that the skin, which is a structural element, in a mechanically structural element, is not sort of hanging on itself like gloves. It's actually connected through a gigantic network of collagen fibers to the bone, which is extremely strong. And so that's what's represented here. In fact, that's a very key part of the fact that our hands are manipulative, is that the skin is actually structurally connected to the bone. So that's what lets us actually grab a suitcase without any problem. And to give you a sense of the capabilities, the load that you can apply to a hand covers a range of magnitude that covers practically 5 orders of magnitude. Now, from the smallest things you can do to the heaviest. Okay, so that's impressive and interesting if you compare that to other senses, like vision and audition, which also cover many orders of magnitude of possible stimulation. So of course the hand is not as capable as the ears or the eyes in terms of orders of magnitude, but still 5 is a respectable number. And it can do it sensually and motorically. So you can cover this space. And so a lot of that, of course, is due to the fact that it's a structural element which has all the right properties to allow that. And a second aspect, which I've been working on quite a bit lately, is the fact that we have sweat glands, which are very numerous on the skin. And what they do is essentially permanently exude water, which keeps us alive because we are made of living tissues. And the tissues have to be wet to be alive. And so if the water was not replenished periodically, then the tissues would dry out and then you would die. And so there's an autonomic system that actually keeps you moist automatically, and apparently plays a major role in at least primate manipulation. It's very important to have wet hands, and that, or at least hand with a certain moisture content, and that is due to the fact that what I represented on the top here is the part of the skin which is the structural element which is in contact. It's called the, well, it has a scientific term, it doesn't matter. It's like a harder part which is made of keratin. And so it's like hair, if you want, same type of material. And when it's wet, it acquires properties which are very unusual and interesting that I will mention a little later. And of course, so basically the sweat system is very important for manipulation, at least for us, in the sense that the water has to exude all the time, reabsorbed, and then what the autonomic system has to do is make up the difference. Now some of it is evaporated. And so that's what it has to do. And not only that, but it seems to play a role also in the fact that whenever I grab an object, the water gets trapped between the object and the hand and modifies the mechanics locally. So that's something we'll be talking about. And so I'll skip the rest of the details in the interest of time. And of course, the hand, of course, is polyarticulated, as we know. It can do a lot of movements. And it has this wonderful mechanical tendon-driven system to move the finger at the right place, and then has its gripping capabilities. In a way, you could think that actually the fingertip could be compared in a sort of loose manner to the fovea in your eyes. And then the job of the hand is actually to move the fovea at the right place in order to detect things that are important for manipulation. But just look at this picture here. It's interesting. You all have looked at your hands when you grab a glass. And that's something special to the primate hand. Whenever you touch an object, it immediately creates a very large contact area with a very small load, very gigantic actually, and copies the shape macroscopically, but also microscopically. So it actually makes a very good grip simply by being there. Automatically. So that's and that picture shows something which is also apparent. When you curl your finger, you can see actually it creases in the distal phalange here, and that crease is actually due to the fact that the tissues are the connective tissues are very abundant. So when I reach the limit, actually they start making buckling the skin because they reach their length, maximum length. And so, so that's things you can observe and become interested about. And of course, not even mentioning the fact that you have ridges and fingerprints, which are made of ridges in the volar parts, in your hands and feet. And I wish I had time to talk about ridges because there is right now in our small circle quite a small scientific tempest to try to decide why do we have ridges in the hands, which is not a very obvious question. Why would the nature had bothered making the reticulated structure inside the volar parts? Good question. So far, I mean, the naive or the textbook explanation is the ridges are there for friction, right? It's called friction ridges. 2 years ago, a fellow published a paper where it actually showed that ridges diminish friction in reality. So actually, if you didn't have ridges in your hand, you had better grip. So why are they there is an interesting question. As far as I can tell, maybe we can talk about it after the talk. I know at least a good half a dozen reasons why they change, if you want, either the sensory or the manipulative property of the hand. So ridges are interesting. And so these are just a few facts that are well known about the biomechanics of the extremity, which grabs objects. In terms of the loading, if you push a flat surface on the finger, it makes a round circle. That's interesting, actually. If you put your finger on a flat surface, then the contact area is very close to a circle, which suggests, actually, that simply the shape of the contact area tells you something about the object in terms of at least its curvature. For those of you who have, like me and Matt, who have some background, you may remember the works of Ron Fearing way back then, who worked on this idea and actually used it in robotics under the supervision of Tom Binford, that goes back some times ago, and actually determined that that was a very useful indicator for the shape of the object that you're touching, simply by the geometry of the contact that is made when you grab an object. And so that's due to the fact that you hardly push the skin in, like you put 1 millimeter displacement to a couple of millimeters, and then you have a very, very, very soft object, and all of a sudden becomes very, very stiff. Okay, so there's a moment where actually this organ becomes like very stable. And so that's useful when you co-contract, when you grab an object. If you want to feel it, then you have a small load. And if you want to actually hold it stably, then you grasp, and then you have a more stable grip. And that's intrinsic to the mechanics of the finger. And also because it's a living organism, they are liquids, which shows immediately that it's viscoelastic, so speed matters. And so in fact, if you push on the hand fast, then it becomes rigid much quicker. Okay. And so that's, whether it's useful in manipulation, I can imagine cases that it's actually quite useful, that you have a harder hand when you load it fast. And that's true at many scales. It's true also at the scale of the ridges. They are very stiff if you shake them very fast. Because of that reason, because they are actually, it's not a simple solid, it is actually a biphasic solid. There is a elastic part, which is the connective tissues, and there is liquid in between. So it's really two phases which are mixed. And so having a biphasic solid gives you new properties that are useful. I was talking about stiffening. One interpretation of that is actually when you run your hand on surfaces, then actually the mechanical interaction occurs at very high speeds, even if the features are very small. And then actually at that speed, the hand is quite hard, in fact. So it's very soft in the low frequencies, if you want, and then hard in the high frequencies. The other diagram is kind of interesting also, in the sense that it takes very little to get the full contact. So that's due to this structural arrangement that we were talking about. And of course, because it's biphasic, then if you load it, then it will creep, it will change through time. And so these are sort of the bulk properties of a fingertip. And they are interesting in their own right. And of course, for each of these different features, you can come up with an explanation or a reason why it's useful, or maybe a problem. But you could think of tasks where actually these properties are come as an advantage. And of course, the hand is a very good sensor. So we saw the case now. It's a good tool holder. And it's a wonderful sensor. It's capable of detecting very small things and discriminating very close objects under many types of different mechanical properties. We were speaking about this with Bobby a few minutes ago, in the sense that your hands are capable of discriminating, I don't know, sub-micrometer details of differences between two surfaces. Simply by running them on objects. So some while ago with Chi Wang here, who is the first author of that paper, who is now a prof in biomedical engineering at Columbia University, we became interested for the objective of making good displays. So that was the objective. A good display for the hand is something that would give you good tactile sensations. We had to find out what the skin properties were, if you want. The same problem you have if you want to make a good optical display. You have some idea about the optics of the eye to be able to do it. And so we made this machine here, which basically is a mechanical tester at a small scale, and it's capable of grabbing 0.5 millimeter square of skin and then loading it mechanically to see how it responds to loading. And because it's a feedback system, we could, by control, make it operate as a isometric device. So something essentially that imposes displacement and you read force out of it, or the other way around, you would impose a force and then see how it moves. And so we did this, and this is what we found. You have here the situation. The way the testing was done was actually by grabbing the skin on the surface and then pulling it sideways. Okay, so the reason for that, it's because it's reasonable to imagine that whenever you grab objects, we have a tendency to focus on, if you want, what's known on the pressure part of the interaction. Like if you want the distribution of forces normal to the surface. But but most manipulation actually involves traction. Now you really lift objects and you slide and from principle of contact mechanics, you actually realize, I don't have time to explain that, but you can easily realize that actually these components are not independent. Okay, they are really part of the same state, mechanical state of an object. So that's why we went for traction and tested the skin in these conditions here. And so here you have two traction surfaces, you have the size here, and then they were disposed in such a way that here we could test for elongation, and then here we could test for shear. And then we found actually that people were very different. You have here the materials property of the skin, at least in an equivalent manner for that length scale I'm talking about here, which are widely different from individual to another individual. But that's not surprising. I mean, it's just look at people's hand. You know, you have very small and delicate hands and big ones, and you have calluses, and you know, this guy was playing guitar, so you have, you know, this enormous extra layer here. But what's shown on the diagram is actually looking at the material properties across and along the ridges. Okay, because they are clearly non-isotropic. You have this visible pattern. And that's what was so surprising is actually when you strain the skin across ridges, then everyone is more or less the same. So that's kind of interesting, actually. So it shows that actually the very geometry of the fingertip is made that even if you build this extra layer of skin, you still remain that elastic component, you still retain that elastic component pretty much intact, okay? So that actually keeps your finger equally sensitive. Very useful role of possibly of the having corrugated fingers. And what's shown in the dash here is actually the behavior of the skin in shear mode. Okay, so that's something interesting. Also, in the shear deformation, all the skins are more or less the same, which is something good, I suppose, in terms of its sensing capabilities. So that's what we learned here, and then we had good numbers about what the skin was like, and so we could go ahead and design our display. Not describe the display today. I'll just focus on the mechanics and then comment as I go. And then in the dynamic domain, the skin that you have in the fingers, of course, as I said, is not a simple elastic material. It's viscoelastic, and it's very much classically described by two time constants in tissues. One which is super fast, so if you actually apply a sudden displacement to the skin, then you get this spike of force, because it actually has a very short time constant. And it vanishes very quickly, and then you have a second one here. So there are at least two time constants in the skin. So what is their role in terms of sensing or manipulation? Again, you certainly could attribute some benefits of having these different time constants. It is known actually that the neural equipment that's sitting behind has also different time constants. So they might actually be well tuned to deal with or take advantage actually of the mechanics of the skin. So this three-parameter model is actually a good representation of what you have in your fingertips. And of course, we replicated the experiment in the opposite causality, which is actually to load the skin with a known force and then see how it moves. And that's what you actually see. It actually creeps along as you load it. And so that's the last part of that study. It was really interesting to see that it really loses a lot of power, energy. These are hysteresis loops that are caused by straining the skin and then restoring it. And then you can see actually in in the slow loops, you have enormous energy loss. If I recall the number, 80% of the energy is dissipated. So whenever you grab something, it mostly goes in heat, actually, in dissipation in the fingers, unless you move very fast. And then later, we also had, because in the lab we have a very intense activity in stimulating the fingers. And so we have to know what the finger is from a mechanical viewpoint. So now we had an idea of what it was from a microscopic level. And then curiously enough, we didn't find any good data for what a finger is in a bulk, as a bulk. You know, what it is like a single mechanical system, a finite, number of parameters. What is it? What is a fingertip? Is it like a complex nonlinear system or something simple? Or what is it? So we went ahead and measure it. And so in order to make a measurement, we didn't find a good instrument, in the sense that when you do a mechanical measurement, it's like doing an electrical measurement. If you want to know an unknown system, you have to call up to a known system, and then you know the unknown system by the difference. That's the principle of any measurement. So when you have voltages and current amp meters, that's what you really do. But in the mechanical world, what you have to do is, if you want to test a system, you have to either make it super rigid to see how it responds in terms of loading, or actually you have to load it with a known load and then see how it moves. Okay, so to have a good measurement, you have to have a probe which is very different from the system you measure, not the same. So mechanically, you have two choices. Typically, what is done in industry, you have a structure and you don't know what the structure is. You impose displacement on the unknown system, and then you measure how it responds from the force of interaction. Okay, so that's called an impedance head. That's what you do, and it has a problem, a conceptual problem, in the sense that if you want to know the impedance, you have to know displacement and force at the same time. And mechanically speaking, there is a problem in the sense that when you build the instrument, the two signals are not located. They have to be dislocated. They are not collocated, if you want. And so what it means is that in the high frequency, it doesn't work. And, or at least you have a phase uncertainty. So what we did is the opposite. Is built an instrument that actually imposed force, known force on the finger, and then measure how it moved in response. So we had to build a probe that essentially had no mass and no elasticity. So that's that was the problem posed in order to make a good probing device. And I can show you actually how to do it. It's not so hard. We went and acquired a very simple loudspeaker, which is operates on the principle of a Laplace force or Lorentz force, depending on which country you are in. The Brits call it Lorentz, the French call it Laplace. And then the advantage of that motor is that actually you have a very good. I mean, if you know the current that goes in the coil, you know exactly what is the force that's developed. But you also can know its velocity. So that's the advantage. You have an intrinsic sensor in there, and then you add an accelerometer, and you add a displacement sensor, which in that case was a Hall effect, and putting all this on a flexure, which would guide the movement in that direction. Then we had, if you want, a probe for the finger. Okay. And the idea was to apply feedback to the system in order to change its impedance or its mobility, rather, the inverse of the impedance. And try to remove its inertia to such a way that it will become smaller than that of the finger. And it can be done, in fact. And that's where, if you do your job in terms of control design, engineering design, you can do it. And you can obtain actually a system that has very, very high mobility, which is, if you want, the inverse of its inertia, very, very high, of a very good frequency range, and then of course has to keep a nice decay in a low range. But what we ended up achieving is a probe that was many, many times lighter, more elastic, and less viscous than the finger itself.
Can you tell whether that motion, is that motion, what's moving? Is it the skin relative to the bone?
Right, so you put your finger on the plate, and the plate is servoed in such a way to have no mechanics, essentially. So now we can actually probe the finger and then measure its impedance accurately. Now to answer your question precisely, yes, that was it. How was the finger interacting with the probe?
I'm just wondering whether your joints are moving, or is it just your skin moving with your joints?
Right. I'll go back because maybe I should have made it more clear. We are interested in what, if you want, when you scan an object, what does the object sees in terms of mechanical loading. So we are looking at displacements that are very small, like a few millimeters, okay? And the result, I'll skip that. The result is actually the finger, to our distress, turned out to be a very simple thing in reality. There's no real complex stuff. It really is a second order system, very much so. So it's essentially, to 100 hertz is essentially elastic, very much elastic. And then after that corner frequency is basically a viscous damper. Okay, very close approximation to a viscous damper. Nothing complex, but there are, the 100 hertz corner frequency is very interesting actually. It shows up in different domains, in fact. It seems like actually the finger has these two modes, like the low frequency mode and the 100 hertz, where essentially is elastic, and in the high frequency mode, where essentially it's a viscous load. And so in terms of haptics, it's very meaningful, at least to me, because when I make displays, now I know what the display is actually stimulating. It's actually displaying this dashboard system with a 100 hertz corner frequency. And I'm very much convinced that actually the brain is very much aware of that, very much. Something is interesting, if you look in the higher modes here, like that's 100, 200, 300, 400 hertz, 5, you have this modal dynamics in the finger, which we attributed actually to standing waves in the fingertip, which is really probably what happens. I mean, the wavelength and the physics are compatible with that hypothesis. And I think these standing waves, why they are standing waves, is because actually when the subject would put their fingers on the stimulator, the slightest movement would modify them. Okay, so they would be fluctuating. They would just come and go, depending on how you moved. And I believe that could be useful for the brain actually as a sensing mechanism. If you want, its bulk physics would actually be very informative in terms of telling the brain what it's actually interacting with. So that's still an ongoing idea. I have colleagues in neuroscience that have picked up on this idea, actually, that actually the higher frequencies are very useful. But you can actually see them mechanically very well in these measurements. And something which is interesting is that if you go through a range of displacements, the three basic mechanical parameters don't change very much, which is a good thing. So it's really very much a linear load that you have your fingertips. And that's true for all subjects. But more astonishingly, if you plot all these three terms of the mechanics as a function of the loading, in a sense, how much I push on the surface, they are pretty much not changing so much. So it's like as if you want your external skin is mounted on ball bearings in a way. So regardless of how much I push, it still have this by and large same mechanical property, which is very interesting actually. And I can tell you, yeah, the inertia is very small. So these are in grams. So basically, even if you grab your shovel, and you squeeze very hard, then your skin at the interface between the shovel and the hand is still free to move, perfectly unimpeded, and perfectly capable of picking up the smallest, if you want, perturbations coming from the tool. Because essentially it's very light and it's free of moving and responding to small displacements. What it doesn't do is respond to big displacements. So that's very cool, I think. Like you have this instrument at your fingertip, which is a very good grabber. It's capable of like pulling tens or hundreds of Newton, and at the same time remain sensitive. So it can do the two things at once, which is a wonderful, piece of mechanical engineering that is right there. And so that's what we learned in doing that study. Of course, all fingers are different, and of course they vary with direction, but that's less of an astonishment. And then later, of course, because our objective, I said, was to turn these studies into something useful for making stimulators, we ask a very simple question. If I have a finger that runs on the surface, like this piece of plastic here, or this cardboard, or this plastic here, which is carbon fiber, what is the transformation there is between the geometry of the surface and then the loading on the skin? I would like to know that, because then if I knew, I would probably be in a position to make good virtual reality. Okay, I could say, okay, here's an object, and then I would synthesize it. But before I can do this, I have to know what is the transformation from at least geometry and material to mechanical activity. So we went ahead and measured it, which is something what we all should do, measure. And then, so that's the setup. We built what's called a tribometer. So a tribometer is nothing but a force sensor, but it's a little special in the sense that to make good measurement, you have to organize it such that you have, say, from 4 to 5 orders of magnitude of dynamic range. Otherwise, you don't really measure frictional phenomena. So you need that range, and it also has to have a very good response in the frequency domain, because things happen over a wide frequency range. And so we took the simplest case possible, which is a piece of plastic, epoxy, which is slightly unpolished, very important. So it has an array of 50 microns. So it's silky if you want, but not smooth. And then it has undulations on it. And then so that's a fairly simple case. Okay, you have this plastic with undulations. What signal does it create? So your guess would be, well, it makes an oscillation, right? And in fact, that's what it does. That's what you measure. You can present the result in that fashion, which is a little unusual, so I'll explain for a minute. What you have on this axis here is a frequency axis, but in the spatial domain. Okay, so these are spatial frequencies from low to high. So from, if you want, big to small, all right? And here you have amplitude here. And the way it was done, it's because when people move their fingers, the velocity is never the same, right? In fact, when you scan, you go from 0 to max to 0 to max, so it's constantly changing. So there is no notion of constant velocity in normal behavior. It's permanently changing. So we had to work out an algorithm that would actually take the velocity of the finger and then transform our signal into the spatial domain, which is actually nothing but a resampling process. But we did it carefully, so we didn't lose any data, and spent quite a bit of time doing this. And what you find is actually something very rather surprising. Whenever you run your finger on a piece of, say, plastic or this or blackboard, each time you do it, the signal is quite different from the previous trial. It's not repeatable. It's but to a point which can be really annoying. Like here, you have a nice spectrum the way you would like to have it, with a big fundamental corresponding to the frequency of the surface, and then some harmonics, of course, because it's not linear. So you have, harmonics developing. But sometimes you get a completely different one, or different distribution of harmonics. I mean, and you can do 100 times, you get 100 different spectra. So so what does it tell you? Well, it's it's a nonlinear system, right? But also it's one which is sensitive to initial conditions, highly sensitive to initial conditions. So whenever I lay my fingers on the surface and I test it, I get a different signal each time. So that's really interesting. How does the brain deal with that? How does it extract information from a signal that's never the same? So there must be irregularities, which are, if you want, hidden somewhere. I'll try to suggest one. Of course, the explanation for this lack of stationarity comes from the nonlinear interaction, for sure. I know the friction, we all know, is nothing but linear. So whatever it does is always interesting. And the regularities actually showed up. We were very disappointing because we had like a 1 week deadline of the conference. But basically the job was simple. You take the 100 measurements, you put them all together, and you do an average, and what do you see? You see a lot of fuzz, and then you see a very nice harmonic signal, okay? Which actually has a harmonic decay that resembles very much that of a triangle wave. So it reminds me of stick slip, if you want. But there's the fuzzy part on it, which is actually the noisy part. And indeed, if you take the same plastic and make it completely smooth, and then you measure again, that's what you do find. You do find this noise which decays at a rate which is on average, always the same. Okay. But of course, from trial to trial, it can be quite different, even if you try to control the condition as much as you can. So in the end, the model is not so hard. In fact, if you think of it in a stochastic manner, if you want to make an algorithm that gives you the sensation of a silky surface with undulation on it, what you have to do is basically create a noise which decays essentially at this rate in terms of spatial frequencies. That's what you have to do. And you had to it a deterministic component where the harmonics actually decay to another rate. And so that's a very simple, very parsimonious model. You have only 2 numbers or 3 numbers to deal with. So it's easy to put in an algorithm. And it's true, when you re-implement this in a computer and you feel it, it does actually feel like it should. So that was a nice simplification, actually, from something complicated. And then later, we continued on that study, and we correlated actually these 2 numbers, alpha and beta, to something which is intrinsically high level, which is how people felt surfaces in terms of how pleasant they were. Like, from sandpaper to nice alpaca wool, and so on. And we did actually find a very high correlation between certain aspect of these decays and then the sensation of pleasantness. So my next sponsor, I hope, will be Dior, or hopefully. I know it's a big business, right? And how much time do I have left? 5 minutes?
Oh yeah, 5 minutes. I guess.
All right, so I'll finish on this study here, which is also was very much mind-changing. Tonner is principal investigator at the University of Catholic of Louvain in Belgium. And he had a former student, a doctor, who had dealing with a patient who has lost their hand in accidents, and the hands were structurally reconnected to the body. And if the conditions are right, the hand live again and reconnect to the brain, but it takes a long time. For that to happen, it takes a year to 2 years before actually the brain re-understands the signal coming from the hand. So in the meantime, these patients have hands which are numb. Okay, so they can move them, but they don't feel anything through them. And but really nothing, like you can really go. And so, and they are completely incapable of, say, grabbing an object or, doing something very simple. Putting a peg in a hole is completely impossible. But part of the battery of tests was actually to ask these patients to rank sandpaper, which is a simple clinical method, which is fine, which is coarse. Okay, so you can, and then Lee Bouton, who was the lead investigator, to his surprise, found that these patients could rank the sandpaper like you and me, really just as well. Okay, no deficit. But you could take a hammer and go like this on the hand. They could do it, and later they went ahead and anesthetized the hand in healthy subjects. You can still do it, no problem. Okay, ranking sandpaper. So that's rather mysterious. How do you manage to do that? Because all the textbooks tell you, no, the skin is the seat where you actually feel roughness. So we went ahead and tried to find how that was possible. And what we did is put a very sensitive microphone in the wrist here, where you have all the tendons running that control the fingers, and then listen to the mechanical noise that's going when you actually rub surfaces like I showed, and doing simultaneous measurements. And then what we found is actually this huge mechanical, activity in the forearm. And if you want to get a sense of it, you can actually grab a stethoscope and actually put it here and then grab stuff, and listen to your arm, and you will hear enormous amount of signal. So the interpretation is actually it's what I was saying at the beginning, the structural organization of the hand, which I briefly showed, with this very large amount of connective tissues and tendons and cartilages, and are actually mechanically transmitting, and those signal propagates high in the anatomy, which actually is very curious, because now if I put myself as in the situation of the brain, and then I'm connected to the body, and whenever I go and do things, there's this incredibly rich and complicated amount of information arising from almost everywhere whenever I do an object, which actually gives some idea of what is the computational problem that the haptic system has to solve in order to be able to be dexterous and rapid and discriminative. So that's very, very interesting. So the lesson here is that the mechanical world, unlike the optical world, is rich in possibilities. Well, the optical world is rich in many possibilities. The mechanical world is even more rich in possibilities, to an extent which is hard to imagine if you don't actually measure. If you simply think about it, it's not sufficient. You really have to investigate. So I'll finish on this. I have lots of yes, that's what I was saying. Why do you do this, right? So that's what I was talking about. Because when you do this, you actually modify the mechanics of your finger. And the reason why, actually, is in this study I did with Tona also. It really has to do with the hydration of the skin. And I can tell you the upshot, because we have very little line left. It really divides the world into two categories. you have a category of objects which are non-porous, like glass and plastic and metal and so on. And these type of material actually trap water when you grab them. And the net effect is actually to increase the adhesion or the friction. But to an extent which is not small. If you put your hand on a sheet of glass, after a few seconds, then the so-called like equivalent coefficient of friction increases by 10. So it's not just a little, it's really very large actually. And so the influence of time and water on the grabbing act is actually much bigger than your squeezing force. But by a huge factor actually. So basically it doesn't matter what you're doing, time is more important. And the second category of objects is the objects which are porous, and they do the opposite. So they actually take water away. And when you do measurement, you actually find that actually through time, then your grabbing capabilities are lower. Okay, which we all know when we read newspaper. First page is okay, and the second page is slippery, and the third. So, and that's true of wood, of fabrics, and you know, all these other kind of objects that you really have to replenish water. And so I'll finish on that. I don't have time to explain the way the measurements were made, but I will encourage you to consult that article in which we collected all these thoughts in one place. And there are really sort of interesting facts about human fingers and what the tribology of the skin does to sensing and manipulation. So a few things that are worth remembering, that the notion of coefficient of friction, essentially believing that is true, is probably a fairly useless notion when it comes to real hands. Unless you've completely lost the water in your hands, it's not a notion that is useful. Okay.
Some people here might realize that Humboldt's law is also Coulomb's law.
Yeah.
So.
And Coulomb's law, strictly speaking, refers to the absence of influence of velocity on the lateral component of the interaction force. And Hamilton's law refers to the absence of connection between the surface and tangential component. So the two names are associated something.
That's not what it says in my book.
Well, in my book, that's what it says.
I will concede.
Because they have to be, they sort of worked on it.
I'm not citing my book as an authority.
So sweat, we talked about this. Capillary forces are essentially very small compared to the others. And instead, plasticization is really the dominant phenomenon. The fact that actually your fingers are more like Play-Doh than if you're on nylon. And temporal dynamics, we talked about this, very important. And then the distinction between the impermeable surfaces and porous surfaces. So with that, I think I spent all my time. I have some really nice theory, but there is no time for it.
Thanks very much.
Okay.
So you have time for questions, right?
Yes, I have time. Yeah, plenty of time.
I have a question.
Yeah.
So when somebody loses their hand and
Right.
you sew it back on,
Yeah.
and you connect the nerves, but they can't be connected the same. It takes a year for the brain to get the, and until then your hands are numb. And so you've got a person there who has a year to learn how to use their hands without sensory
Well, basically, well, I'm not a clinician, so I'm not going to answer that question precisely.
So this would be very interesting to see how do they use their hands differently than we do.
I'll ask Ligoton. Yeah. My feeling is that they don't use it.
Really?
Well,
we have a big hand pass service.
Right, so yeah,
and
you may have
here they're writing using the iPhone. They get
so they have compensatory mechanisms.
they get their feelings access, but it does get.
But what about when they don't have their feeling? Are they using their hands then?
In the beginning, the hand pass by he says it's a paperweight.
Right, exactly. Yeah. It's good analogy.
It takes about a year. Well, it takes a number of months.
Yeah, if it goes well. Yeah.
But they can move the muscles. They can use the muscles of their arm immediately. But it takes them a year to get the full motion of the muscles in your fingers and so on.
But I don't understand that. So there's this videotape which people keep pushing at me, you know, like the Johansson videotape where the person they
scratches a match. Yeah, with a dumb finger.
She has a hard time striking a match. But actually, it's not that hard a time. You know, it's like it takes her 30 seconds instead of 2 seconds.
Yeah.
But on her first trial, she does successfully strike a match like in 30 seconds. So you would think somebody that's been able to practice, that's had the use of their hands, but not the sensors.
You probably know better, but there's also the notion of compensation.
Yeah.
So if you have 2 hands, then you use the one that works.
Well, we should take somebody and tie that hand down for years.
Yeah. Okay.
So I want to come back on your comments about bridges because you did many nice friction measurements. So can you come back and say what would happen if you had bridge versus no bridge in your finger? And how would that affect friction or adhesion?
Yes. Ridges here. Actually, that's one of the possible roles. What is shown here is a cataneo contact. What it means that when you have 2 objects in contact and when they start sliding, they don't transition from no sliding to sliding state in one single step. It's done through a dynamical process, which starts from the periphery. And it's quite interesting to see actually that when the finger starts sliding on glass, the effective contact area becomes smaller. And so that actually enhances the cataneo phenomenon. So that's could be one of the reasons why the ridges are useful. My favorite explanation was actually provided by of Warman and Ennis, who showed that actually the ridges diminish friction by doing precise measurements. And they provided a nice discussion where they showed they interpreted the presence by the fact that you have a manipulative organ, and of course it's subjected to high loads, and because it's a layered system, if you overload it, then it delaminates, which is what happens when you have blisters. Okay, so you really have to have hands which are not delaminating when you clean your house. Okay, otherwise it would be a. And so the one of the mechanical solution to delamination is actually to not have constantly oriented layers. You change the direction regularly. And so that's really a good explanation, because what they really do, if you go back here to the earlier diagram, now if you have a load at the surface, and then you have the fibers that are pulling here, then actually what they seem to be doing is actually reorienting the load lines in the direction of the connection and preventing delamination. So that's a really nice explanation, and I believe that's probably one of the most plausible, in fact. But there's also a role for water distribution, probably. In a simple case, if you have too much water on your hands, then they become too slippery. So it's like treads on your car. You have to have a channel for for regulation. And of course, there is a camp that believes that the ridges are there for sensing purposes. But it could be both, or maybe, yeah.
What if they're just epiphenomenal? They're just the
Could be.
result of the Meissners and their structure. I mean, the Meissners have plugs. And
Yeah.
They plug in and something else pops.
There is a monkey species who have them in the tail. So
Is
it,
it Meissners there?
I don't know, but they have ridges in the tail, and they live mostly in trees and hanging from the tail. So this delamination concept is very, I think it's very powerful.
Another quick question. What's the effect of skin oil? You didn't mention about skin oil. You mentioned about water, but what about skin oil in the finger?
I didn't have, yeah.
Skin oils.
Ah, the oils, yes. Yeah. My colleague, tribologist, would have an answer for that. I'm not going to answer it now, but it's true that actually sweat is not complete only water. But the major effect of the sweat is actually to plasticize the surface. And that's, yes, of course, there is other salts and oily components.
You were talking about standing leaves on slide 15, I think.
Yeah.
And so the speed of sound
Right.
in water is 1,500 meters per
Yeah,
second.
right.
And at 300 hertz, it's much bigger.
Right. But right.
The speed of velocity is much slower.
Yeah. Yes, because there are, as far as I can tell, 3 types of waves that can establish. And the pressure waves are certainly not the one I'm talking about.
Okay.
They will be shear waves, actually.
they're much
Yeah,
slower.
much slower.
Okay.
And perfectly compatible with the...
Well, thank you again.
Yeah.
I certainly learned a lot.
So,
We have to learn the same things over and over again. Oh yeah, look.
you want to...